As we did with relativity, let's take a slight detour into a little bit of mathematics of quantum theory to explain why, if this is the way the universe really is with both wave and particle properties, why don't we see matter actually waving at our scale of the universe? The math that's involved is what's called the de Broglie wave equation. French physicist named Louis de Broglie derived this in 1924, and it's simply an equation for calculating the wavelength of any object based on its mass and how fast it's moving, its velocity. And notice that in here is Planck's constant. Now remember, Planck's constant is a very, very small number, 6.626 times 10 to the negative 34. So if you were to imagine what's the wavelength of a bus? And I actually did this, a friend of mine and I, during first year university, after our physics midterm exam, when we had done the de Broglie wave equation, it was our last exam of before the Christmas break, and we'd both been studying madly for days and days and days, and we were in kind of a silly mood. So on our way home, we were joking about all the stuff we'd learned in physics, and we decided we were going to calculate the wavelength of the bus we were riding home. So we actually went up to the front of the bus and we stared at the speedometer to check the speedometer, and we asked the bus driver, what's the mass of a bus? And fortunately, he didn't order us to get off at that point, but you can actually do that. So imagine a 2,000 kilogram bus. That's its mass. It's traveling at 60 kilometers per hour. This is a pretty big mass compared to subatomic particles, a very big mass compared to subatomic particles, but it's a very slow speed compared to the speed of light. So if you plug those numbers in, here is Planck's constant, a very small number on the top. We plug in our 2,000 kilogram mass on the bottom and the speed in meters per second. And what do you calculate? The bus does indeed have a wavelength, but the wavelength is this. This is obviously way beyond human perception, and that is why we do not see wave-particle duality. Just like we didn't see length contraction because the effect is so small at the speeds we're used to, the speeds we exist at, we don't see the wave properties of matter because they're so small at the large masses that we're used to, the large masses compared to the subatomic particle. If Planck's constant were a bigger number on top, then we would have longer and longer wavelengths, and at some point you might have, if Planck's constant were big enough, you might actually be able to see these waves. But in our universe, as it is with Planck's constant, the value that it has, the wavelength of a bus is there, but it's absolutely unmeasurable and imperceptible to us. But what if you're dealing down in the subatomic world, the ones we can never get to, we're just too big? Well, a typical electron has a pretty high velocity, and it's got a very, very, very small mass, typically 9 times 10 to the negative 31 kilograms. You plug those numbers into the de Broglie wave equation, and you actually get the wavelength of an electron as being 0.25 nanometers. Now that's still very small, too small for us to see if we could even see an electron, but it's actually a pretty long wavelength, because remember, the wavelength of visible light is 750 to 400 nanometers. This is on the same scale. In fact, it's smaller, shorter than the wavelength of visible light, which means we can apply this to an important technology. Because remember that we see things, we see anything by bouncing light waves off of that object. Well, the smaller the object is, the shorter the wavelengths have to be that we bounce off them. So we get to a point where we look at objects that are so small that the light waves, the 400 to 750 nanometers, have such long wavelengths that they just go right around the object, they don't bounce off it, and we can't see them. So there's a limit to what you can see with light. When an object becomes too small compared to that 750 to 400 nanometers, it actually becomes invisible with light. But electrons have shorter wavelengths, and that means they can bounce off even smaller objects than light can. And this is how we've invented the electron microscope. In a light microscope, we bounce light waves off things, and we can bounce them off things as small as bacteria, and we can see bacteria. But viruses are much, much, much smaller. They're too small for light waves to bounce off them, but they're not too small for electrons with their wavelength of 0.25 nanometers to bounce off them. And so we can use the electron microscope to see much, much smaller things than light microscopes, things like viruses, things like specifically the SARS-CoV-2 virus, the one that causes COVID-19 and is forcing me to do these lessons online for you.